Hello. So now we're going to graph this absolute value equation. So the first thing we need to identify is the domain. Okay. The domain for this absolute value equation is from negative infinity to infinity. And remember that the domain is the set of all the x values that make sense with the algebraic expression that we're attempting to graph, or with the algebraic expression that represents the function that we want to graph. And that's, of course, depending on whether we want to look at it from a function perspective or from a equation perspective. So strictly speaking, the domain refers to the function defined by this expression. But as I mentioned earlier, you know, if I'm graphing this equation, it's the same as if I was graphing this function. And so that's why we talk about the, and so that's why we talk about the domain of this equation, because we're really saying the domain of this function. But I want you guys to know that both of these things, they don't necessarily mean exactly the same thing. This is more a statement about a collection of points that satisfy some criteria, namely the set of points x, y, that make this equation true. That's the perspective of the equation. And the perspective of the function is for some input, in this case the x, we get some output. And of course, usually we make functions when we want to talk about something that has some practical significance. The cost of making X cars, some practical scenario. Anyway, so strictly speaking, again, whenever we talk about the domain, since domain is a concept associated with a function, we are looking at the function that has the algebraic expression that we want to graph. And but so anyway, I wanted to make that point because it's kind of like it's kind of like it's a minor point more than anything, but I wanted to make that very clear. So now with the absolute value equation like this, or absolute value function, when we want to calculate the range, we know that it's best to first locate the corner point. Okay. So now, just to break the monotony a little bit, I want to remind you of one way of looking at an absolute value equation like this that might enable us to get the corner point or vertex quickly, and we're going to do that right now. And then I'm going to show you the way we've been doing it so you can compare those techniques. Okay? So here is the fact. If an absolute value function can be written in this way, okay, f of x is equal to some constant a times the absolute value of x minus h plus k. It has corner point or vertex h comma k, and opens up if the a is positive, and it opens down if a is negative. Okay, and I want to point out something else here. You might have noticed that here the a greater than 0, a less than 0. What about a equals 0? If a equals 0, 0 times this x minus h in absolute value term will go to 0, and we'll just be left with f of x equals k, which, if you recall, represents a horizontal line. It's no longer an absolute value function because it zeroes out the absolute value term, and so that's why why the case a equals 0 is omitted from this. As written, this is correct. And you can use this whenever it is in this form. You can use this rule to get the corner point. And I also want to make something very clear here. Notice how here, wait, what? Okay. So notice how here the h inside is minus, the k on the outside is plus, and in my corner point or vertex, my h is plus and my k is plus. That is to say, in my vertex, the sign of the x coordinate is opposite. The sign in the vertex is opposite that inside of the absolute value term, but the k sign is the same. Okay? And now let's look at it in this practical example. Okay? So this is a fact you want to learn. Okay? Oh yeah, and let me also make something else clear. Later on, we're going to talk about function transformations. And so you're going to see that this expression, again, what I'm about to say right now, we're going to understand it better later. But I'm just going to state it for completeness. That you're going to see how we can justify this using transformations, and that it's going to be a transformation to the right by h units, the x minus h, if h is positive. And it's going to be a translation up by k units, and it's a vertical stretch by a units, but not precisely in that order. We'll talk about the ordering of transformations later and all that other stuff later, but I wanted you to know that this formula, it has a logical meaning that comes from a discussion we're going to have later on, but right now you can write it down as a fact. If an absolute value function is written this way, then it does in fact have a corner point, namely this one, and if a is positive, it opens up, and if a is negative, it opens down. So let's look at that together here. So I'm looking at this this equation. I can see, aha, my a is positive 2. Okay. So let me write that down, that it opens up. Okay. 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 Look at this, x minus 1/2, x minus h. I mean, yeah. So therefore here, my corner point, okay, is going to have x coordinate positive 1/2. And then look at this, because you notice how in our equation here, it's x minus 1/2. In our expression over here, it's x minus h. You see? So if you compare those two, then you can see that the h must be 1/2, okay? And now let me also make a point here. If this had been x plus 1/2, I know that you all realize now that the h would be negative 1/2. But since here it's x minus 1/2, and since here it's x minus h, the h must be 1/2. And so that's why it's my x coordinate of my vertex. Now what about my y coordinate? Here I have a x minus h plus k on the outside of the absolute value. And what's my y coordinate of my vertex? Just k. Here I have x minus 1/2 plus 2. So the 2 must be my y coordinate of my corner. Okay? And just to be clear, if this had been a minus 2 instead, it would be a minus 2 here. Okay? Okay. So now, let's remember how we were doing it before to remind ourselves of that technique too. So we recall, so I know we already got the corner point, but I'm going to do this again to review what we've learned so far. To find the location of the x coordinate of the corner point, we set the inside of the absolute value term, which is this one, equal to 0, and solve for x. Okay? So let's do that together here. The inside of my absolute value term is x minus 1/2. Okay, I'm going to set it equal to 0. And then I'm going to solve it for x. In this case, you can see that you just add 1/2 to both sides. Right? I add 1/2. And then I get that on the left-hand side, I'm just left with x. Then, what's 0 plus 1/2? That's 1/2. Doesn't that look familiar? Indeed, that is exactly the x value of the corner point that we got previously, using the formula behind me. Okay, so now how do we find the y coordinate? Okay, we find the y coordinate by plugging into the function. Okay. And so here, we remind ourselves, to find the y coordinate of the vertex, we evaluate the expression. What expression? The expression that defines the equation at the x coordinate of the vertex. So let's do that here. So I'm going to do y equals 2 times the absolute value of, what's my x in our case? 1/2. That's my x coordinate of my vertex. Minus 1/2 plus 2. Now what is 1 minus 1/2? I mean, 1 minus 1/2. What is 1/2 minus 1/2? That's 0. So I get 2 times the absolute value of 0 plus 2. What's the absolute value of 0? That's just 0. So that's just 2 times 0 plus 2. And of course, we know that 2 times 0 is 0. So this is, of course, 0 plus 2, and that's just 2. We can see that this completely confirms what we got previously using the equation behind me. And so now that we have confirmed that we have gotten the corner, we're going to discuss the range. Okay, let's do that now. So in order to find out the range, first of all, we know it opens up now. We know that. We know that. So we're going to draw a little cartoon here. It's going to look like this. Now here's an absolute fact you have to remember. For the absolute value equation, for the graph of the absolute value equation, the corner point is your maximum or your minimum, depending on whether it opens up like this or if it opens down like this, okay? Here, of course, if it was opening down, this would be your maximum. Okay, your maximum would be your corner point, the y value of the corner point. And here, which is the case for us, because ours opens up, this is going to be our situation. This value, the corner, is going to be a minimum. Okay, so what do we mean by that? We mean that if I were to plot this point, it would be 1/2, comma 2, right? And if I look at my y-axis, okay, you know that, of course, here this would be 0. If this value is 2, then I know that the graph, since it's going to go up like this, the range will be from 2 to positive infinity, right? On the other hand, let me just draw this like this over here. Now over here, let's imagine if the graph were to have opened down like this instead, and let's say it had the same y value, right? Then you can see here, if I go down, that's to negative infinity. So if it had looked like this, which is not the case for this problem, but I'm bringing this into the discussion just for us to look at this, right? If it had been like this, you can see it would go from negative infinity because the graph is opening downward, and it would go to 2, right? So in this case, the range would be from 2 to infinity, which is our case. The infinity is always with an open parenthesis, and the 2 here, and the bracket here next to the 2 means I'm including the point 2. Because in fact, we know it achieves this value. It achieves it here at the vertex, at the corner point. Now over here, if this had been the case, which is not, but you can see here, the range would have been from negative infinity to 2, so it would have looked like this, okay? Because it would start from the bottom, negative infinity, and will go all the way up to 2, okay? So let's write down the solution to ours, which is from 2 to infinity, like this. Now, let me also make a brief discussion here with our cartoon. By the way, the reason why I'm calling this a cartoon is that I'm drawing this just to capture a tiny bit of basic facts to make an evaluation of something. But it's not necessarily the absolute value graph that we're going to draw at the end, which is going to be more detailed, very carefully drawn, etc. Okay? But I want you also to get used to drawing tiny little graphs like this if you just need to have a tiny bit of insight from the graph. Now look at this. X-intercepts. This is a perfect example of such a situation. We know that the y value here is 2. Okay, so let's get rid of this part here. Okay. Let me show you this. So, yeah. So, if you notice, the y value here is 2. The graph opens up. Will this graph ever touch the x-axis? We ask ourselves, what is required for the graph of a function or the graph of an equation to touch the x-axis? It has to have points where the y value is 0. We can see from this cartoon that since it opens up and since the y coordinate is already 2, it will never touch 0 or any negative value. So therefore this absolute value, this equation, the graph of this equation will never, will not have any x-intercepts, okay? And so here, using this cartoon, we were able to eliminate the possibility of x-intercepts. So we're going to write here, not applicable, or just as our way of shorthand for they don't exist in our case. Okay, but just for kicks, we're going to see what that means algebraically. right? We're going to verify that algebraically so that we can know, okay? So let's continue this way. So again, just for kicks, we're going to recap. To find the x-intercepts of the graph of an equation, or function respectively, depending on what you want, we set the y equals 0 and solve for x, okay? So here, I'm going to set my y equals 0. So let me put this expression on the left, and then I'll put the 0 on the other side. See, I set my y equal to 0, and I'm going to solve for x now, or I'm going to try to. First things first, I want to get this plus 2 to the other side. What am I going to do? I'm going to subtract 2, subtract 2. Aha. So I get 2 times the absolute value of x minus 1/2 is equal to negative 2. Is the absolute value term by itself? No. I'm going to divide both sides by 2. We can see that this is x minus 1/2 in absolute value equals, what's negative 2 divided by 2? That's negative 1. And now we can see why there were no x-intercepts. We can see it from an algebraic standpoint, okay? If we had done this procedure first to try and find the x-intercepts, because maybe we were looking for the x-intercepts specifically, we would have done this first. We wouldn't have gotten the graphical insight we got earlier. But once we get to this part where we see that the absolute value of a number is claimed to be equal to a negative number, then we know that there is no x that will satisfy this, because when we take the absolute value of this inside, it'll become positive, right? So what does that mean? That means that if there are no x values that satisfy this equation, then that means there are no x values that satisfy this equation. And what does that mean? That means that the location, that there is no location for x-intercepts. Points with given x coordinate that have y coordinate 0, okay? And so yeah, so now we have seen the algebraic verification that in fact there are no x-intercepts. So now we're going to find the y-intercept, okay? So to find the y-intercept of an equation, we set x equal to 0 and solve for the y. So let's do that together here, okay? So y is going to equal 2 times the absolute value of 0 minus 1/2. You see I set the x equal to 0, and then plus 2. So now 0 minus 1/2 is just going to be negative 1/2. Okay, so it'll be 2 absolute value, negative 1/2, plus 2. Now what's the absolute value of negative 1/2? It's just positive 1/2. Okay, so 2 times positive 1/2 plus 2. Okay, now you might ask, okay, David, what's 2 times 1/2? Well, 2 times 1/2, the first thing I do is I don't know how to multiply a whole number with a fraction. But what I can do is I can convert this 2 into a fraction by setting it as the numerator and 1 as the denominator. So it's going to be 2 over 1 times 1 over 2. Okay? Now, how do I make now do I know how to multiply 2 fractions? I do. The product of 2 fractions is the fraction whose numerator is the product of the numerators of the fractions being multiplied, and whose denominator is the product of the denominators of the fractions being multiplied. So here, 2 times 1, that's 2. 1 times 2 is 2. And we can see what's 2 over 2? That's just 1. So I come back here and I say, aha, this is going to be 1 plus 2. What is that? That's 3. So then I can come over here to my list of like necessities, and I can see, aha, for the y-intercept, I have 0, comma, 3. Okay? Okay. And so now, finally, we are going to make a table and we are going to graph this. Yes, it's going to be so beautiful. Yes. Okay, so now we are going to plot this, okay? And so right now, let me see here. Dun, 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 dun. Okay. So as I mentioned earlier, one of the things that the absolute value, one of the properties of the graph of the absolute value, and of course the corresponding function, is that it is symmetric about the vertical axis that would go through the corner point or vertex, just as though we were in a parabola. So here, if I imagine here, let me see here, 1, 2, 3, 4, 5, 6, 7, 8. I'm going to plot my corner point first, which is one half along the x and 2 along the y. If you noticed, I drew the x coordinates big, so I could draw the 1/2 very clearly. Okay. And I know that my 1/2 is plotted at the point 2. So 1, 2. So that'll be right here. Okay. And then I also know from what we saw that my y-intercept is at 0, 3. So that's 0 along the x, in other words, on the y-axis, and 3 on the y-axis. Notice this though. If I go 1 to the left along the x from my vertex point, and that leads to a point having a y-coordinate of 3, then by symmetry, I can flip that over, right? And I go 1/2 to the right, which will be at x value 1, I'll have a point with y equals 3. Okay? In other words, this point is 1, 3. Okay? This is my corner point. And by the way, notice how I got that point. I got that point from just reflecting along the axis of symmetry. Let me draw that in here. In other words, although it's usually, although usually I don't like to think about it in this way, I want you guys to notice that we do have an axis of symmetry that is the vertical line that goes through this corner point. So we write a vertical line as x equals, and then whatever x value we want the vertical line to go through, it'll be x equals 1/2. So what I want you to realize is this. If I draw it in as a dotted line, remember this is not part of the graph, okay? But I just want to put it in just to make this point absolutely clear. I went 1/2 to the left to get to my y-intercept, which has y value 3. So what I did was I went 1/2 to my right, and I will also have a point with y value 3 by symmetry, okay? And so now, finally, we can draw this graph. Because the absolute value is just 2 lines, well, not 2 lines, 2 pieces of lines that meet at the vertex, we can draw it in, okay? We can draw with one side, we just need 2 points, and with the other side, we just need 2 points, because 2 points determine a line, and that's our graph. And if we wanted to, we could make a longer table to have more points and so on. But what I want you to take away from this more than anything is how I used the symmetry property of the absolute value to get a point on the other side that I didn't have, and that was just all we needed to finish this graph. I hope you all have enjoyed this example, and I'll see you again soon. Thank you.